Hello, everybody. It's great to be here. It's an honor for me. So today we're going to talk about zirconia from fabrication to application. Thank you very much for interest, Steve. So I did a study dentistry back home in Iran in a school named Mashhad University of Medical Sciences. So School of Dentistry in Iran, unlike US, is 6 years, and we started at the age of 18. So did that 6 years, did social services, private practice, then moved to Birmingham, Alabama to do masters in dental materials. So that's where I learned a lot of stuff from Dr. Burgess, Dr. Lawson. They mentored me, and after that, I joined LSU to do pros. And now I'm teaching at LSU in Department of Prosthodontics. So today we're going to talk about zirconia. Today's lecture, we can divide it into two parts. We're going to talk about zirconia itself, and then we're going to talk about cementation of zirconia. We're going to cover these topics. First of all, we're going to go and see where zirconia stands among all different ceramic materials that are available in the market right now. Also, we're going to check how zirconia is manufactured and how we can classify zirconia. Right now, there are so many classifications by many names, and we're going to see how we can clear it and make a unified classification for zirconia. Then we're going to go over the cementation and see what type of cements do we have. We're going to answer the question that can we really bond to zirconia, a very it's a hot discussion always. Can we really bond to zirconia? We're going to see if that's possible or not. And then we're going to go over some tips and nuances on bonding to zirconia. And at the end, we're going to talk a bit about what are the benefits of bonding versus simply luting a zirconia crown. All right, let's start with classification of ceramics. We can classify ceramics in general based on different parameters. For example, we can classify them based on the fact that they're monolithic or they have been layered with feldspathic porcelain. We can classify them based on their fabrication method, if they are milled, they are pressed, or if they're layered. Or we can classify them based on their microstructure. We're going to go over the classification based on microstructure here because that's going to give us a lot of information on how we can really understand the properties of these ceramics. So based on the microstructure, we can define three types of ceramics. We can define a group that are predominantly glassy. They're the most static ones that we have available in the market. We have particle field glass ceramics, and we have polycrystalline ones that are the strongest ones. And the goal is to see where zirconia stands in this classification of ceramics in general. Let's talk about predominantly glassy ceramics. So they have amorphous structure. It means that they don't have a structured phases within themselves. If we assume these marbles are the molecules of the ceramic, they are distributed in a very random way. So they're not creating a pattern, in other words. So the predominantly glassy ceramics, they have this amorphous structure that does not have any pattern. Now, what are the examples of these are aluminosilicate glasses, which feldspathic porcelain falls into that category. And they're well known for being used as veneers on top of zirconia, like PFZs, or by themselves as veneers. The next type of ceramics are particle field glasses. Particle field glasses, they have a glassy matrix, like the other ones, but it's reinforced with some filler particles. Now we can see the green marbles or the glass matrix that they have some patterns embedded inside them, the blue marbles, which are actually the fillers that are used in this glassy matrix. So in this category, the reason that we have the filler particles is that they wanted to improve the mechanical properties and control some of the optical properties of the ceramics. That's why they added these filler particles. Now, what are these filler particles? They're mostly crystalline, and some of them are glasses with higher melting point. Now, we know one specific one that is very famous in the market, that's lithium disilicate. So lithium disilicate is actually the filler particle that is embedded inside the glass matrix, and the name of the filler is lithium disilicate, and we know the ceramic restoration in general with lithium disilicate. We have other types of pillar like lucite, aluminum oxide, and mica, which are older versions. And the most famous one, again, is now lithium disilicate. Then we have the third category of ceramics, which has polycrystalline structure. So they have a densely packed atoms. So they're created by having a pattern. So you can see we have these blue marbles that are forming a pattern. And within the structure of these polycrystalline ceramics, this pattern is repeated over and over and over. It's going to create a mass of this pattern that subsequently provides us a very higher amount of strength. Now, they're usually tougher and stronger than glassy ceramics. They have less translucency than the glassy ceramics. And the example of them is alumina and zirconia. So zirconia falls into category of polycrystalline ceramics, and it has high strength. And now we hear about translucent zirconia, the improved translucency and all this stuff, and we're going to go over that, how that is possible. Now, how zirconia is fabricated. So essentially, zirconia has two sources. One source is a stone named badolite. So badolite is just zirconia, it's pure zirconia, zirconium oxide purely. And unfortunately, we don't have that much sources of badolite in nature right now. So that's why mostly zirconia is fabricated and manufactured from zircon sand. So zircon sand has some silica impurities that needs to be purified, and after the purification procedures, we're going to have zirconia powder, which can form into any form that we want. Now, the most commonly way that zirconia is advertised and marketed right now is with a disc shape that simply they compress this powder into a disc form in order for us to be able to use it and mill our prosthesis. Now, there are new ways and technologies now available, which we're going to talk about it later on, that changes this also manufacturing procedure. Now, we know that zirconia is called by many names out there. For example, we hear translucent zirconia, we hear conventional zirconia. So how can we really scientifically classify zirconia? Let's classify it based on how it's manufactured and what it's composed of. If we do that, we're going to see the first generation of zirconia, which was produced a long time ago, has around 4 to 5 weight percent yttria, and it has around 0.25 weight percent alumina. In the first generation, like lava frame, they observed that the translucent is really opaque. It's not a nice and beautiful and aesthetic restoration. It's really opaque, so they use it mostly for substructures. And the reason they found that is kind of attributing to the fact that it's not translucent would be the alumina that acts as impurity. And in the grain boundaries, it deflects the light, and we cannot have a nice translucency. In the second generation, in an attempt to increase the translucency, they essentially reduced the amount of alumina without changing the amount of yttria. So they found that, okay, if we reduce these impurities, we're going to have higher translucency, and that's how they modified the first generation to second generation by decreasing the amount of alumina. But still, the amount of yttria is the same. Now, in the third generation, a different route of changes was used by manufacturers. They started playing with the amount of yttria. They bumped up the amount of yttria to 7 to 9.5 weight percent, and in that way, they tried to modify the crystalline structure of zirconia by increasing the amount of cubic phase. So we always hear about cubic zirconia. So as a matter of fact, cubic is one of the phases of zirconia that we will find higher amount in the third generation when we compare it to the first and second generation. In the first and second generation, we have around 5 weight percent yttria, which is equal to 3 mole percent yttria. That's why they are called 3Y zirconia. In the third generation, the yttria content is around 7 to 9.5, which is equal to 4 or 5 mole percent. That's why they're also called 4Y and 5Y. Now, we need to remember that again, cubic is not a type of zirconia. It's is one of the crystalline structures of zirconia that we can increase it by increasing amount of yttria in our structure. The examples of second generation that are available right now in the market are Vita translucent. These are just examples. Katana HT or ML, they are second generation. They have 3 mol% yttria. And the third generation examples are Vita extra translucent and Katana UTML, same company. They have different products which has higher amount of yttria, higher amount of cubic phase, less amount of tetragonal phase, and subsequently higher amount of translucency. Now, there's a new generation of zirconia that is coming to market now, that is available right now, and that's Zirlux Transition. So Zirlux Transition is a unique product that is different in terms of manufacturing procedure, which we're going to elaborate a bit more later. So essentially, Zirlux Transition falls into the third generation, the newest generation of zirconia, which has become more translucent by changing the amount of yttria. Again, based on the mole percentage of yttria, the second generation is called 3Y because it has 3 mol% yttria, and third generation is often called 4Y or 5Y because based on the amount of yttria, they have 4 mol% equal to 7 weight% yttria, or 5 mol% equal to around 9.5 weight% yttria. Now, when we look at the Zirlux Transitions instruction for use, we can see that there is a more than 90% zirconium oxide in the structure, and it's more than 7% yttria in it. So again, we learned that 7 weight% yttria is equal to 4 mol%. So that's why Zirlux Transition is a 4Y zirconium, but it's a bit different than a regular 4Y because it has different amount of yttria within this structure that makes it a different product. At the same time, it doesn't have that low of a flexural strength that we can expect, which is around 1200 megapascal. So let's elaborate more a bit on that. How do we compare mechanical properties of a so-called translucent zirconia, the third generation that has 4 or 5 mol% yttria, in comparison to the conventional and lithium disilicate? So we did this study back in 2018 at UAB. We compared 3Y, 5Y lithium disilicate. In order to compare them, we made zirconia squares and we made zirconia bars. We used the squares in order to check the wear, translucency, bonding, and we used the bars in order to check the flexural strength. So what we observed is that when we compared 3Y to 5Y zirconia, we can see that the 5Y has higher cubic phase. Subsequently, it has higher amount of light passing through it. We don't go deep into why that. So at the end, it has higher translucency than 3Y. In terms of bond strength, they acted the same. So essentially 3Y and 5Y, same bondability. And in terms of wear resistance, they also perform similarly. However, in terms of flexural strength, 5Y was inferior to this 3Y. Now that we have a new generation, further down the road, we started having 4Y zirconia. Now we have a 4Y zirconia. How that means in terms of translucency, bond strength, wear resistance, and flexural strength. So we can expect a sweet spot between translucency on one hand and flexural strength, because if you want to have higher translucency, you need to have more cubic phase, and higher cubic phase means less tetragonal phase and lower mechanical properties. So I believe that 4Y is kind of a sweet spot in between 3Y and 5Y, because it has adequate translucency, at the same time it doesn't lose that much of the strength, which is very crucial for us in the clinic to have a long-term longevity of our prosthesis. We don't want it to break. So 4Y falls into a very sweet spot in that term. Now, when we look at Zirlux Transition, it has its unique technology that creates these changes and variation between cervical region and the incisal region. So in the cervical region, we would have less amount of yttria in comparison to the incisal part, which we would need usually higher translucency. So that's why as we go gradiently, it moves toward a different amount of yttria. That's why also in the instruction for use, it was mentioned more than 7%. It didn't mention exactly 7%. So that means that less amount of zirconia in the incisal area and more in the cervical area. That at the same time creates a nice balance of shade because there is different concentration of zirconia. So that's really unique in that term. And still it's a simple single puck. So that's very nice. Now, we talked about tetragonal and cubic phase. And we always hear about self-healing properties of zirconia. Let's see how that translates into the fact that how these zirconias behave. So this is a SEM image of zirconia. These are the grains that you can see they're packed by each other, and the boundary between them is called grain boundary. Is very important for us in terms of optical properties. Now imagine in this zirconia a crack happens. So essentially, zirconia have this so-called self-healing property that is able to not let this crack propagate further. How does it do that? So simply, tetragonal phase transforms once there is a stress into monoclinic phase. Monoclinic phase has higher volume, around 4% more volume than tetragonal phase, and that higher volume kind of pressurize the crack and doesn't let it propagate further. And at the end, if a crack happens, that property of tetragonal to monoclinic phase transformation doesn't let the crack propagate further down. Now, again, we know that 3Y zirconia has higher amount of tetragonal phase, 5Y has a higher amount of cubic phase, and subsequently has less amount of tetragonal. So we can expect that the 3Y has higher healing ability, if we call it, than the 5Y. And now when we have a 4Y, we have something in between them, that it has a middle range of that self-healing property. It's not losing it that much, but still it has higher amount of cubic phase than the 3Y generation. That's why it's more translucent. So I think that 4Y is a nice balance between the mechanical properties and the optical properties of zirconia. Now, there's something very crucial when we talk about zirconia, and that's sintering. So sintering of zirconia is extremely crucial in terms of how it's going to affect the final product. Let's see how it does that. So when we have a green state zirconia, there are particles, remember that traditionally they were pressed, the powder was pressed together in order to form a disc. So this pressed powder, there are spaces between them. Once we put the zirconia inside the oven, each of these particles, the outer surface, start to melt. And as they melt, they come together, they bind together. And once it's cooled down, we can see that we have a dense final prosthesis that has lower volume and is denser. So this is the whole idea of the sintering procedure. That's why in zirconia we have something named enlargement factor or whatever it's called by the company that says, for example, in this example, it's 1.2275, means that if we have a 12.275 millimeter height puck, after sintering it, it's going to become a 10 millimeter puck. So that enlargement factor depends on how dense on these particles are together and how much water they have. Now, you can see how much the diameter of the disc has been shrunk after it's been sintered. Now, what has happened in the Zirlux transition based on the technology that it has is that these particles are together, are dense together. So instead of being far apart, they're more densely packed side by side. So this technology is able to provide this amount of density, which as a result, we would have less shrinkage percentage in the zirconia disc. So what that means is that we're gonna need a less amount of zirconia in order to cut the same prosthesis because later on it's gonna undergo less amount of shrinkage at the end. So when we go to the sintering cycle of Zirlux transition, it's very important to read this very carefully because we're going to later on discuss how the sintering temperature is going to affect our zirconia. You can see that it's recommended to ramp it up to 1500 in a regular, for a single crowns, up to 30 per batch. That's also very important to kind of read that, because sometimes we have series cycles that are really fast. I don't know, 90 minutes, 1 hour, but it limits how many crowns you can put in the same batch. So it provides you up to 30 single crowns in one batch, which takes around 4 hours if they're all singles. And it's very, very important that we realize that the temperature of the oven needs to reach that 1500. If it does not reach that 1500, if the oven says it reaches 15, but actually does not, it's going to affect everything in your zirconia. It's going to affect its mechanical properties, its optical properties, and everything related to that zirconia. So it's extremely important to have a calibrated oven when you're going to sinter the zirconia. So there's this study in 2017 that checked how the sintering temperature affects the microstructure and mechanical properties of zirconia toughened ceramic. Now, they increased the sintering temperature by increments, and they checked the mechanical properties of the zirconia based on each sintering temperature. What they found is that as they increase the sintering temperature, the porosities and the pore sizes decrease. In other words, the zirconia became denser as the sintering temperature increased. So you can imagine, if you underfire your zirconia, you're going to have a restoration that has higher porosities and higher pore sizes, which will later on lead to possible higher rate of failure, higher rate of discoloration, and other stuff. Now, they also observed that it increases the relative density of the material, and it increases the flexural strength. So it's very important to know that if we increase our sintering temperature to that ideal recommended by manufacturer temperature, we're going to have a stronger zirconia. They also observed the fracture toughness increase, and the surface hardness by Vickers test also increased. So that again shows how important is that to make sure that your sintering oven reaches that temperature that needs to be reached, and maintains that, and be able to sinter zirconia. Even if you have the best zirconia in the market, if your sintering oven does not perform well, you're going to have an inferior product at the end of the day, and dentists won't be happy, the lab tech won't be happy. So it's very crucial to take care of that sintering temperature and having no impurity in your sintering oven. The other factor that's going to affect your crown would be the optical properties of the crown. This is a Zirlux crown that sintered by Master Edwin in LSU School of Dentistry. He made two similar Zirlux transition crowns. This one, he sintered it 10 degrees less than the one on the right side. Depending on the quality of monitor, you can find out that the one on the right has higher value, it's brighter, and it's exactly the same zirconia. The only thing changed is the sintering temperature only changed by 10 degrees. So you can see how much it can affect the final shade of your zirconia crown. And if you look at it from black and white background, you can appreciate the fact that the right crown has higher value. So again, we go back to the same discussion. Your sintering oven is very crucial. If you get the best zirconia, still you need to figure out what's the optimum sintering temperature. You need to find out how much hold you need to have. You need to calibrate your sintering oven so you don't get you get constant good result at the end. All right, now talking about cementation. So cementation is also a dilemmatic discussion right now. There are discussions that, can it really bond to zirconia? Is it really reliable? Does it really make sense to bond to zirconia or not? So let's go check it. First of all, let's classify the cements that are out there in the market. So generally, we can classify cements into two broad types. We can classify them into luting cements or bonding cements, or we can classify them based on their temporary or their long-term cements. Let's go over the luting cements. So there are so many wording in terms of cements. Sometimes it's called luting, sometimes it's called cementing, sometimes it's called bonding. So what's the difference? Here, for the sake of discussion here, we're going to call luting a non-resin cement. So the examples of them are glass ionomer, resin modified glass ionomer, zinc phosphate, and polycarboxylate. So these are cements that they're going to lute the crown, and they're not necessarily bonding to the ceramic restoration in order to hold it in place. On the other hand, we have resin cements that we can further classify them into total etch, self etch, and self adhesive, and we're going to go over the differences between these as well. Now, luting cements are only providing for us micromechanical retention. However, on the other hand, resin cements provide chemical bonding that provides that chemical retention also to the crown that does not exist in luting cements. We can also further classify cements into temporary cements and long-term ones. The temporary ones are like zinc oxide. We know them as temp bond or temp bond Ne, and temporary resin cements like Temrex TNE. We use it when we don't have enough retention or restoration in our temporary. So we need to make sure the temporary stays in till the next visit. So we use Temrex TNE. Just we need to be careful. It has some resin inside it, so it can bond to the composite and can pull it out after we take out our temporary. Not good. So then we can have long-term cements like zinc phosphate, polycarboxylate, resin modified glass ionomer, and resin cements. So these are permanent cements. They are not gonna, we cannot take the crown in and out easily if we're gonna use these kind of cements. All right, so let's talk about resin cements. How can we classify them? So I'm gonna here bring some example of some resin cements available in the market. For example, we have Panavia V5, we have Reliance Ultimate, and we have GC Link Force. So all these three cements, they're self-etch cements. What does that mean? So it means that the components that they have, they enable the clinician not the need for etching the restoration or the tooth separately. So in other words, there is a chance that I can just use these products without etching the tooth prior to bonding and get a good bond. So that means that there would be extra component that I need to use. For example, in terms of Panavia V5, I need to use a tooth primer on the tooth structure, and I need to use a ceramic primer in the intaglio surface of my crown in order to get the bond that I need to get. When I use Reliance Ultimate, I need to use a Scotch Bond Universal cement adhesive. And when I use GCEM Link Force, I need to use the primer that is going to be used in the intaglio of the crown. And I'm going to use the Premium Bond that is going to be used on top of the tooth structure. Now, again, these can be used in two modes, total etch and self-etch. Total etch means that I'm going to etch my tooth with hydrofluoric acid, with phosphoric acid, sorry, for 20 seconds, then I'm going to use these products, or I simply don't etch my tooth structure and I just use these products. But we have another generation of cements that are self-adhesive. It means that they have all of these inside them. And when we talk about, for example, Panavia V5, the equivalent would be Panavia SA. Reliance Ultimate is Reliance Unicem 2, and GCEM Link Force would be GCEM Link Ace. So these self-adhesive, you can see also on the GCEM Link Ace is a self-adhesive resin cement. It means that they don't have any extra component that you need to use in order to bond your crown. You can simply grab one of these, inject it in the intaglio without the need to etch the tooth and just put it in. So they're very simple to use, much more clinician friendly. So you're going to lose a bit of bond strength when you use them, but it's really not significant. So in terms of applicability, much easier, makes more sense. Now, there's always this question, can it really bond to zirconia? So essentially that comes from the fact that when we have lithium disilicate, we know it as a fact that glassy ceramics like lithium disilicate, we can simply use hydrofluoric acid to make them rough and then use a resin cement to bond them really well, and they really work. We know them as a fact for many years. Now, when zirconia came, at first we saw so many debonding in the zirconia crowns. So they come off, they didn't bond well. So there was always this question, why zirconia does not bond? Does it really bond? Now let's go to the answer. Can you really bond to zirconia? So everything started from this molecule. It's 10-MDP. This molecule was invented to get bond between zirconia or ceramics and the tooth structure or resin cement. Now, how does this 10 MDP works? So imagine we have a surface of zirconia, which is filled with zirconium oxide on the surface, and we have the bonding or adhesive or primer that has MDP inside it. So MDP has two sides. One side is ceramic lover and the other side is resin lover. The ceramic lover has phosphate group that kind of really wants to go and bond to zirconia, and the resin lover has a tendency to go and bond to resin cement. So when we apply MDP containing primer, resin cement, or adhesive, we're going to have a bond between the MDP and the zirconia surface in one side, and the other part that loves the resin cement from MDP and the resin cement. So that's a link between the zirconia and the resin cement, and that's how it's going to create a chemical bond between these two. Now, then the question becomes, do we really have a proof that applying MDP creates a bond between zirconia and resin cement, or is it just a theory? So the answer is within this publication. So in 2012, this group tested the bonding of prime zirconia ceramic, wanted to see if we really can use it, it can bond to zirconia or not. So they used zirconia samples, they primed it with MDP contained primer, and they did a test named time of flight secondary ion mass spectroscopy. So essentially what it means is that they scraped a part of the surface in order to get some molecules out of the surface of the zirconia after it's primed with MDP, and to see if there is any really bond between the zirconia and the MDP primer. So essentially when they scraped it off, they found that different fragments of the bond between the phosphate group and the zirconia. So remember, there was a phosphate group in MDP that loved to bond to zirconium oxide, and there was another side that loved to bond to the resin cement. So once they used the MDP primer, they found that some fragments of bond between phosphate and zirconia, and that kind of proved that there is a chemical bond between zirconia and MDP. And they went further as well. So they exposed the zirconia surface after priming with MDP to harsh situations like boiling water, like strong acids. And again, they did the same time of flight secondary ion mass spectroscopy test, and they found again they have the POZR bond inside the fragments that were scraped off from the surface. So that kind of showed them that when you prime it with MDP, not only are you going to get a bond, also you're going to get a durable bond that's not going to get affected simply by harsh situations out there. Now, how can we really bond, for example, to a zirconia crown like a Zerlux crown? So there's some nuances into bonding to zirconia, which I'm going to go over. So we know as a fact, one of the first steps we need to do, we need to create surface roughness in order to bond to zirconia. In other words, we need to make the surface rough and then bond to it, so we would have a better bond. Now, how can we do that? Traditionally, we use aluminum oxide, alumina, in form of particles, and we use those particles, we air abraded, use air pressure, and we bombard the surface, and we create that surface roughness with those alumina particles. Now, there are newer versions of how we create surface roughness. Maybe you hear from here and there that there are acids that are available in the market that essentially can etch zirconia surface for bonding. So these acids are a combination of hydrofluoric acid, hydrochloric acid, sulfuric acid, and other acids that are pretty strong. So it's not easy to use them without having a very confined situation that can suction these acids out. So it's not that easy to create that environment. Then once we have the acid, we need to embed the zirconia crown inside the acid for maybe an hour or maybe 2 hours. And after that, we need to glaze again the surface of the zirconia, because essentially we embedded the whole zirconia inside it. Now, sometimes maybe there is a question. Does it really worth to do etching rather than sandblasting? And the reason I'm saying that is that there is a discussion that whether when we have a 5Y zirconia, so we know that 5Y has less amount of tetragonal phase. So when there is a crack, it has less potential to prevent that crack to propagate. So now when we sandblast it, we use aluminum particles and we bombard the surface, we may create some cracks that does not have that self-healing to close it and not letting it propagate. So in other words, some may say, hey, maybe this acid etching is a better solution than using aluminum particles and doing the air abrasion. So let's find out, does it really worth to use the acid or not? So there's this study by a good friend of mine, Dr. Sadizadeh in University of Buffalo. So they wanted to check that how the etching solution of zirconia can affect the shear bond strength between zirconia and resin cement. So they created zirconia discs. They divided into 4 groups. In the first group, they used 50 micron alumina and they air abraded the surface. In the second group, they just etched it. They embedded inside the acid for maybe 2 hours, and after that they took it out and they tested the bond. Then the third group, they first alumina abraded the surface, then they etched the surface with acid. And in the fourth group, first they etched the surface with that property, that acid, that strong acid, and then later on they air abraded it to see how these affects the bond strength. After they bonded the cylinders to the surface of zirconia with resin cement, they thermocycled the samples for 1,000 cycles to age them, and then they measured the shear bond strength. So essentially, they cracked the cylinders to see how well they were bonded to the surface. So this is what they observed. So you can see that when the control group, just using alumina, just doing air abrasion, it gave them around 10 megapascal of the shear bond. When they just etched it, it gave them around 9 megapascal. When they alumina abraded and etched it after that, they got around 9.5, and they got higher when they used the etch and alumina, first etch, then alumina abrasion. But at the end of the day, none of these were significantly different from each other. So it means, in other words, they were the same. So how that translates, and let's look at how they concluded the results of this study. So this is what they mentioned. Considering the hazardous nature of the zirconia etching solution, airborne particle abrasion with 50 micron alumina particles remains the surface treatment of choice. In other words, hey, there are too many loops to jump through to etch zirconia, like having a special acid, investing on that, having a special place to isolate that acid so you make sure we don't harm anybody, and then leaving it in for a longer period of time. Then we have to glaze it again. So too much work to gain the same bondability if we can just use for 10 seconds alumina particles. So again, if we have this discussion that can we etch zirconia? Yes, we can. Does it worth it? Definitely not. It's too dangerous, it's too hazardous, and at the same time, it's not too rewarding. Not gonna make our bonding twice as if we just use aluminum particles. There will be other studies also we're gonna discuss later on that to answer the question, if we use aluminum particle, are we really damaging and we making the crown weaker or not? We're gonna talk about that. All right, let's talk about the second tip. So how long after creation of surface roughness should we bond? So this is very interesting. In other words, there are 2 reasons that we do sandblasting or air abrasion with aluminum particles. One reason is that we want to create that surface roughness. The other reason is that we want to clean the surface and increase the surface energy of that intaglio surface of the crown. So increasing surface energy means that the surface is going to be hungry to absorb MDP or phosphate of the saliva or anything around it, the dust. So there's the surface energy is so high that it can absorb everything from the much more than before from the environment. So here's a question. So if I ask my lab tech to sandblast it for me, the lab tech is in New York, they're gonna mail it to me, the crown. It's gonna take a couple of days to get here. I'm gonna open it, and then I'm gonna try it in the mouth. Really, am I getting the same bond as if it was sandblasted right away, right now? Let's answer that question. This is a study that recently published in Dell Materials Journal 2021. very new, and it talks about the influence of elapsed time between airborne particle abrasion and bonding to zirconia. So essentially, they air abraded zirconia discs, and they waited 15 minutes, 1 hour, 4 hours, 24 hours, and 72 hours after that to bond to the surface of that air abraded zirconia. So after they stored them until tested, they stored them for 3 days or 150 days. Essentially, they bonded some cylinders to the surface of the zirconia that was sandblasted 15 minutes before, 1 hour, 4 hour, 24 hour, or 72 hours before that. They bonded some cylinders on top of them. Then they stored the sample for 3 days or 150 days. In other words, they aged the bonding between the cylinder and the zirconia surface. And then they tested the tensile bond strength. Let's see what they observed. So this is what they found. As you can see from the left to right, as we go to right, the amount of holding the crown before bonding it after sandblasting increases. You can see that when it's 3 days, so when the bond is young, it's maybe not huge differences, maybe 24-hour huge difference. But when the bond is aged, over time, we can see a huge difference between them. If we had sandblasted right away and we had bonded it right away, we would have had way higher bond strength, around 40 megapascal. But if we wait 72 hours after sandblasting it, we're going to have 25 megapascal. So that's a huge difference between two, just based on the fact how long we waited until we bonded our zirconia surface. So highly recommend that when you have a zirconia crown, I understand that it's possibly sandblasted before, but always the lab techs recommend to dentists, hey, if you have a micro etcher by your side, after you tried it, you checked everything, just briefly sandblast it very quick. It's going to take 10 seconds, 10 seconds of sandblasting, 20 seconds of rinsing it with water and pressure. Not a big deal. Then we're going to jump to a very fresh surface. We're going to have way better bondability, and the bond is going to remain high for a longer period of time. So that's going to be a huge change. And again, the reason is that once we sandblast it, the surface energy is so high that it's going to absorb everything from the surrounding. The dust in the lab, later on saliva in the mouth, so it's going to absorb everything. So it's best to refresh the surface. All right, so let's go over another nuance in the bonding. So clinicians usually try the crown. For example, they receive this Zerolux crown. They're going to try it in, make sure everything fits. It's lovely, perfect, fits good. Now let's bond it. What's going to happen? How should we clean it? In other words, once we try it in the patient's mouth, we take it off. Can we just use water spray for 20, 30 seconds and pressure and just spray it? And we make sure we clean everything and then we bond it, or shall we do something else? Let's find out. So there's this study published in 2015 that they checked various cleaning solutions on saliva contaminated zirconia for bond strength. Now they had again zirconia discs, they air abraded the discs, and in the control group they didn't contaminate it with saliva, and in the study groups they contaminated with saliva. Don't ask me how. Anyhow, so they contaminated the surface with saliva, and in the control group they didn't need to clean it. Now in the study groups they needed to clean this contaminated surface. In the first group they just used water spray. They water sprayed it for a specific amount of time in order to clean the inside. Second group, they air abraded it again with aluminum particles. Third group, they use IvoClean, a solution, to clean it. Fourth, and other groups, they use different solution in order to see what chemical solution can help bond better to the surface. And then after that, they measure the shear bond strength, how well that resin was bonded to the zirconia surface. Let's see what they observed. So you see that in the control group, they found around maybe 10.5 megapascal of bond strength, and then they just cleaned it with water. They got half of the bond they would have gotten without having a saliva contamination. So it's very crucial to know that if a clinician thinks that just using water is enough to get rid of all those phosphate groups from saliva, it's very wrong. They need to use something else. That something else can be air abrasion with alumina particles, can be IvoClean solution, or can be sodium hypochlorite. So either of these. So this study showed they can really bring back the bond to what the control group was. Now, let's talk a bit cleaners that are available in the market. We have one from Katana, it's a Katana cleaner. We have IvoClean, and again, we have the other choice of using air abrasion. I personally prefer that because that's fast, that's easy. I create again surface roughness, I increase the surface energy again, I bump it up. I don't know how long the crown was in the lab. It's not nobody's fault, it just takes time. So I really prefer using air abrasion. But if you have IvoClean, how do we use that? Why IvoClean is helpful? All right, so we remember that zirconia surface had zirconium oxide, and the phosphate group of MDP was going to bond to that surface through the zirconium oxide. Now, in saliva, we also have phosphate groups, and the phosphate groups in saliva are going to block those zirconium oxide surfaces that were going to be bonded with MDP, for example. That's why we have solutions like IvoClean. So IvoClean contains an oversaturated solution of zirconium oxide that kind of is hungry to get all those phosphate. They're scavengers. They're going to grab everything and catch it to themselves. And that way, once we apply the IvoClean for a specific amount of time, then we're going to rinse it. We know that the phosphate group are all removed from the integrity of the crown. That's how IvoClean works. All right, last tip. Why do we really bond to zirconia crown? Is it just because of retention? So we know that when we have a prep that is less than 3 meters in height, when it's more than 20, I don't know, 6 degrees in taper, so we don't have enough retention based on the tooth, if it's a molar, premolar, whatever. That way, we would be recommended always to bond it to make sure the crown don't fall off. But is it really the only reason that we need to bond a zirconia crown, or is there any other reason? Let's find out. All right, so we did this study. We had zirconia crowns. We made 80 zirconia crowns from 2 types of zirconia, 3Y and 5Y. And I don't go to details about aging procedure. The goal is the non-age groups. And half of the non-age groups, we use resin modified glass ionomer to lute them on the die model, and the other half use resin cement to bond them to the model. And the model was from Lava Namic. Now, what we observed is that, and after we bonded them or luted them, we simply cracked these crowns to see how well they can hold the forces until they fracture. All right, so let's see how the fracture load was different between them. So essentially, we expect from the fact that 3Y has higher tetragonal components phase inside it, it has higher mechanical properties. So we really expect 3Y crowns would be stronger than 5Y crowns, and they're going to hold higher forces before they break. So we observed that as well. So if it was a 3Y crown, it could hold more than 5,000 Newton before it breaks. And when it was 5Y, it could hold around 3,000 Newton. Now, when we bonded them, the interesting part happens here. So the 3Y crown got stronger to around 8,000 Newton. And the 5Y got as strong as a bonded 3Y. So this study was so nice to see that, oh, really, bonding is not just for holding a crown in place. It's also to make the crown stronger. That has been proved already in lithium disilicate. And this study and other similar studies, we're going to go over one more as well right now. They prove that using a resin cement actually not only increases the bondability, retention, it's also make the crown stronger. Now, this is a study published by my mentor, Dr. Lawson at UAB in 2019. So what they did, they made zirconia crowns from 3Y and 5Y, and in half of them, they did surface treatment. In the other half, they just used alumina air abrasion in lithium dice, and half of them, they luted them. The other half, they bonded them. Luted, they used Relix Luting Plus. which is resin modified glass ionomer, and in bonded, they use Relax Unison 2, which if you go back, it's a self-adhesive resin cement. So it doesn't need any additional components. And the lithium disilicate, they etched it or didn't etch it. Now, they did the same thing. They fractured the crowns and they check if the fracture load changes, if they bond it or they lute it. So this is what they observed. So when we move from the left to right, we can see that the 3Y crowns that were bonded, they have higher fracture load than the first column that were luted. So they found the same results. If you bond your crown, is it a 3Y or 5Y or lithium disilicate? Lithium disilicate you have to bond. 3Y or 5Y, the zirconia, if you bond it, we're going to gain extra amount of strength within the crown that we wouldn't have it if we just lute it. So does that mean that every time we should bond it? Maybe not. Sometimes if the isolation is a problem, if you bond it, you're going to gain at even lower bondability, even lower strength than by just using bonding agent, bonding resin cement. So in those cases, maybe there are some cases so deep, the isolation issues, we can benefit from using a resin modified glass ionomer. But in other cases, really bonding gives us too much help. So why not? Side note, in this study, they found also when you sandblast the intaglio surface of the crown, even if it's a 5Y, you really don't see that it decreases the fracture load of the crown. So sandblasting causing cracks that may fail it, maybe. So what they did is that they aged the samples, and when they were aging, when they were fatiguing them, 2 of the 5Ys were sandblasted, broke. So maybe, but essentially when they withhold all through the fatiguing cycles, they didn't break, and they broke to the same levels as a non-sandblasted 5Y zirconia crowns. All right, so that's it for today. Thank you all so much for being with me. I really hope we learned something together. Looking forward to any questions coming up. Thank you all so much.
Thank you, Dr. Nejat. At this time, we're opening up to any questions. So far, I don't see any, so I'm just going to give our attendees a moment just in case they want to type something in to ask you. But all of us here at Zahn Dental hope you enjoyed this very informative webinar. Please let us know what topics you'd like to learn more about in the future, and take a moment to take a look at Zahn Academy to take a look at any upcoming educational events that might interest you. And so far, we don't have any questions, so I think maybe you answered everybody's questions in your presentation. Dr. Nejat, thank you so much again. Oh, wait 1 second, I do have one. Right now, the question is saying, etching Emax crowns in the lab.
So is the question is that, shall they etch the Emax crown in the lab or not?
That's what I have. Etching Emax crowns in the lab is the question, I guess. They want to know whether or not they should be.
Right. So
is it acceptable?
Right. So it's traditionally done, right? And if the lab is kind of in-house, it's not far away, there's no big deal about it. But if the crown is going to stay in the lab for a while, it's going to absorb all the dust, and then the clinician is going to see the patient in 2-3 weeks after receiving the crown. So possibly it's better to recommend to the dentist, hey, I etched it a couple weeks ago. Now that you want to bond it now, it's better you etch it again. There are also studies on lithium disilicate that shows also lithium disilicate has the same issue, that over time, because once we use the hydrofluoric acid, we're going to gain a lot of surface energy. We're going to have a hungry surface that can absorb everything. And lithium disilicate is way more dependent on bonding than a zirconia crown in terms of its strength, because it also becomes stronger. So it's really highly recommended that if the etch has been done a long time ago, or it has been in a situation that you're not sure, just simply etch it again for another 20 seconds and then use that.
Okay, they also want to know, should they do that before immediately sending out to the dental office?
That's a very good idea. That's a very good idea. So the moment you're ready to ship it, before that, etch it, then put it in a sealed envelope or a pocket, whatever, and then send it in that box. So that's a very good idea.